Okay, so I probably don't have to give you this introduction. I do it anyway. Gravity is the least understood fundamental interaction, and I think many of the open questions in contemporary science are related to gravity. Huge intellectual activity going on worldwide, both on the theory side but also on the experimental side. We're working in gravitational waves, so that's the dynamical part of gravity, and the entire universe is filled with gravitational waves. It has a very low coupling constant, so it's difficult to generate and also very difficult to detect. We put that positive in a way that saying it's an ideal information carrier, almost no scattering, no attenuation, and the entire universe has been transparent for gravitational waves. So it might be our only chance to look to an era in the very early universe. And also right now with the first results, you can see it's impacting fundamental physics, but also cosmology, astrophysics, astronomy, nuclear physics. So it is quite impactful. The person that realized that you can actually detect it with an interferometer is Ray Weiss. Before that, also people working on bars and Weber bars were active. But the main realization was that you need to build kilometer scale devices. Otherwise, you have no chance of seeing it. So that's what Ray did. The first detection came in 2015. I was completely calibrated that the first detection would be on a binary neutron star, because after all, we have seen these sources and we know they exist. But it was kind of surprising that it was this type of black hole merger event. Some interesting things about that the combination of masses determines the signal that you see. The maximum frequency in the signal is given by 1 over the total mass. And in the Poisson-Doning expansion, all these phase coefficients are known up to 7th order in general relativity. And one last thing which is remarkable is that if you measure the strain at your detector, and you can look at the signal, determine the frequency and the derivative of the frequency, it gives you the distance. So in that sense, you can, it's interesting for cosmology. Of course, then you also need the redshift, and there are several ways to try to approach that. I'm from the Virgo collaboration. So Virgo is already collaborating with LIGO for, I think, at least 15 years. We have an MOU. We have joint data analysis groups. Virgo exploded in the last several years, more than doubled in size. And many groups from particle physics joined the experiment. And I think 16 countries are involved right now. And here you see it on a map. Before I was in Virgo, so up to stuff like 2005, I was in LHCb at CERN, B-Physics. And I can tell you it's quite a steep learning curve, both on the data analysis, but also in the instrumentation. It's really different than what I was used to in nuclear and particle physics, because everything is very interrelated and it's not so sequential as you have it in nuclear and particle physics. If one detector doesn't work, then maybe you cannot do a certain particle ID or something else. But if something doesn't work in an interferometer, then it's game over. You have to go back and fix it. So this is Virgo. Virgo as an interferometer was not available in 2015. We were still upgrading it, but we joined the second run in 2017. So the first measurement we did on the 14th of August. So we were running then for 2 weeks. And that was the first detection where all 3 interferometers saw the signal, and we could use that in order to measure the polarizations of gravitational waves. So there we got from the experimental side clear a signal that these are tensor, it is tensor polarized, which I find interesting. It's a fundamental property of space-time, and you can address it with these interferometers. So then 3 days later, we got this famous event, the binary neutron star. I know exactly where I was and what I was doing. And now you have heard a lot about that, so I will not talk about it. But many things are possible with gravitational waves. And I will not use this talk to talk about it. In the meantime, Kagura joined in 2020, February 2020. So that is an underground detector, 1 kilometer underground in the Kamioka mountain. It's also like Virgo, an interferometer with an arm length of 3 kilometers. The LIGO interferometers are 4 kilometers long, and that gives a certain advantage. And also the Kagura detector has cryogenic mirrors. So that is another way. In that sense, it looks more to the low frequency detector of Einstein Telescope. Now, in the meantime, we have done 3 observation runs, and in total we collected 90 events. So it goes quite rapidly, and some of these events are very interesting. Here you get an overview, because what we do is once we get a signal, we have an event, we immediately release it to the public, which is again also very different than what I was used to in nuclear and particle physics, because there we sit on the data and we do our own analysis, but this is impossible in this field because astronomers have to follow up, have to look at it, and these are transients, so it has to happen immediately. Also, our data is open, our codes are open. We even give workshops to teach people how to use it. And that is, I provide the information here. So if you're interested to do your own analysis and see if we are doing things correctly, then this is completely possible. So the outlook, this is Virgo. And Virgo is a so-called dual recycled Fabry-Perot interferometer. So that means Fabry-Perot arms, and essentially you have a finesse here of about 450. So essentially you amplify your sensitivity to phase differences this way. You recycle the power because you tune the detection system to a dark fringe, or very near a dark fringe, which means all the light goes out in the direction of the laser again. So you might as well throw it back into the interferometer. And in this way, you amplify the power by about a factor of 50 that you store. We also, and we only implemented this in the last year. We also now in Virgo have signal recycling. LIGO already had that in the previous science run, and Virgo has this also right now. So if a gravitational wave is detected, it appears on this output port over here, but you might as well reflect it back into the interferometer. The interferometer will work as an optical spring and gives you enhanced sensitivity to your signal. So that is also what we installed. Yeah, here you see a view of one of these optical components. So these are quite sizable. Here you see a mirror in Virgo. Of course, it has to be so-called free-falling, and that means that there is a tremendous vibration isolation system used in order to decouple it from the ground. So essentially, it's decoupled in all 6 degrees of freedom, but it's still hanging, of course, on a wire. But also in the vertical, there is vibration isolation.
Can I ask a question here? So how do you ensure it's freely falling, even if it's kind of tethered, right, in various directions?
Yeah, so essentially what you do is you use mass spring systems, and but we use inverted pendula. So not a normal pendula, but like inverted pendula, which gives you an anti-spring effect. And then on these inverted pendula, you hang pendula. And then pendulum typically does vibration isolation in 3 directions. So you need additional systems which take the other 3 degrees of freedom. And in Virgo, we use so-called magnetic anti-springs to do the vertical vibration isolation. So it's all based on mass spring systems, which are tuned to very low frequency, so tens of hertz, or tens of millihertz, and then above that resonance frequency, you start gaining for one unit 1/f². But then we cascade many of them. So it falls down very rapidly, and already at let's say 10 hertz, you get 10 to the 12 suppression factor. So it's hanging on a wire, but if you would touch it, it would freely float also in the vertical direction and in all the angles.
And how would you compare this kind of technique with, say, drop? I mean, of course, in this case, of course, drop tower would not be possible, but this is a very long term, right? It's freely falling for all the time of the detection.
Exactly. Yes. Yeah. Yeah.
And what is the residual acceleration? Would you know? 10 to the power minus what is achieved here?
No, at least more than good enough in order to measure gravitational waves. So measure displacements of several times 10 to the minus 24.
Okay, no, that's fine. Yeah, okay, thank you.
But the problem is below a certain frequency, it doesn't work anymore. You have the resonance frequency, and below the resonance frequency, you don't attenuate. And also, we do part of that. So mostly in Virgo, we do everything in a passive way, and we have very weak controls on the system because we don't want to inject any control noise. And you could never do this actively, because if you do it too much actively, you introduce all your sensor noise, and that will be overwhelming. So you have to always make a combination of passive and active.
Okay, thank you.
Here you see the beam splitter of Virgo, and the same. So there is this tower of 12 meters high, full of vibration isolation systems. We call them the super attenuators in Virgo. And here you see the noise budget. So the total is in black of advanced Virgo. You see at high frequency, it's quantum noise. Essentially, this is shot noise, which you at low frequency will see as radiation pressure noise. In the intermediate range over here, it's coating noise, coating Brownian noise. So we are always working on improving our coatings. We have a huge activity on that. And at the lower frequency over here, it's the blue one, is suspension thermal noise, because you need to hang these objects on wires, and they have noise. There is also in green here the gravity gradient noise, and you see it's not a dominant noise source. But of course, this is not static. If you are in a winter and you have storms, etc., this will go up by an order of magnitude. This is not something that is always there. So essentially, we're working on all these noise sources at the moment. So there's an upgrade program going on at this moment that started in 2020, and for the next run is hopefully starting in December this year. We have implemented part of this upgrade. So we will have tuned signal recycling, should double our, and high power laser, should double our sensitivity, which is 60 megaparsec right now. We have frequency dependent squeezing that is installed. We had already frequency independent squeezing in the last run, but now we added a filter cavity of 150 meters to make a frequency dependent squeezing. And we are implementing also Newtonian noise cancellation systems.
One second. So these units, why is this kind of unit MPC?
Yeah, sorry, I should have said that. This is the BNS range. So this is the distance at which you can detect the merger of a binary neutron star, and then averaged over all sky locations and average over all orientations of that system, and then measure with a signal of a noise of 8. So it's integrated over the frequency range, because these BNSs, they start slowly and they go through your entire sensitivity plot, and then around 1.6 kilohertz, they merge typically, and even giving higher frequencies when they merge. So this is a kind of complicated number, but that is the way we use it in LIGO, Virgo, and Kuiper. And of course, this, if you are very interested in only low frequency sensitivity, where Newtonian noise is important, then this number doesn't tell you a lot about it, because it weighs much more the high frequencies than the middle frequency. So this is the next run. We'll start at the end of the year, December. That is the hope. And then again with upgraded sensitivities for LIGO and Virgo. And here you see the sensitivity targets, where after we run 04, say during 2023, we will break again, probably for a year. That has not been decided yet. And then we run 05. LIGO then should be at their design sensitivity. That is what they hope. And for Virgo, we prefer to give a range. We are not so certain that we can get that far. We need, in principle, more commissioning time. These are some happy people that installed the frequency-dependent squeezing. I show that because the filter cavity was built at NICA. And here you see the mirrors. So in the second upgrade phase, we will go from our 42 kilogram mirrors to mirrors that are more than 100 kilograms. So that means a big upscale, and also you cannot carry these mirrors yourself anymore. So things have to be done robotic and etc. And then we still use LMA in Lyon, which is essentially the only laboratory worldwide that can handle these objects and code them. And these mirrors are absolutely fantastic. If you take one of these mirrors and you amplify them to the size, let's say, of Groningen or Amsterdam, then the flatness is within the thickness of a human hair. It's absolutely beautiful. So third generation. So
can I ask a very kind of naive question there? So the mirrors kind of look like lenses to me, like they look. In the picture, they were looking transparent to me. Maybe this is a...
Oh, no. Yeah, this is a foil which is on top of it, which is just a protective coating. And okay, once we install the mirrors, the last thing we do is that we take that foil off.
I see.
So and then it is it is transparent, which is again strange for a mirror because a mirror should reflect. But it reflects indeed for infrared, but not for visible.
I see.
So here you have Einstein Telescope and Cosmic Explorer. The good news for Einstein Telescope is that now it's on the S3 roadmap. That was decided in June last year. So that means we have now a 10-year window to realize this facility in Europe. And it's beautiful, I think, from the science point of view, but the problem with it is it's very expensive. It's a €2 billion object. So that is what we are working on hard right now to get this project in reality. So there's also an activity in the US. It's called Cosmic Explorer. So Einstein Telescope is triangular in shape and has an arm length of something like 10 kilometers. This is Cosmic Explorer. There are two detectors. One is 40-kilometer arms and one is 20-kilometer arms. So they're two different ones. So the long one is more optimal if you want to study the lower frequencies because it's long and that way more sensitive. The shorter one allows you to study ring down effects. So around something like a kilohertz up to 5 kilohertz, it has better sensitivity. So that's why they chose this. Einstein Telescope is again a European consortium. So there's an agreement signed by 41 institutions right now. And it's coordinated at this moment by INFN and NICF, but we are moving into a new type of governance. So that is what we're trying to set up, similar to how CERN is being operated. So by a council with ministerial representatives and scientific representatives. But that is all work in progress. Here you see the information on the conceptual design study and the upgrade of this. This was made in 2020. And it's a triangular configuration. So why that? Because we have multiple detectors. And if you want to fit as many detectors as you can in a given size of an infrastructure, a triangle is best because you can overlap your detectors. You see, that's what we're doing over here. And then we need to site these detectors underground because the seismic noise is 2 to 3 orders of magnitude less when you go underground. Every detector is made out of 2 interferometers, a low frequency interferometer and a high frequency interferometer. And so schematically, you see again the Fabric-Bureau cavities, the power and signal recycling over here, filter cavities and squeezing, all of that is applied. But low power, heavy mirrors and cryogenic mirrors in the low frequency detector, and high power and room temperature mirrors in the high frequency detector. So if you split it up in these 2 bands, then you get this sensitivity curve for the low frequency one, this for the high frequency one, and this is then combined into one sensitivity curve for Einstein Telescope. So Cosmic Explorer again is different in this sense. They try to use one interferometer and make it as broadband as possible. And essentially it boils down to that you cannot realize the low frequency sensitivity in the same way as we want to do it with Einstein Telescope. Of course, you can argue, these few hertz over here on a range of 10 kilohertz, why do you care? But I hope to convince you that this makes sense. So Newtonian noise comes in. If you look at advanced LIGO, then in black you see the sensitivity as it is measured. And in these colors, you see all the different contributions, noise sources that are making that sensitivity curve over here. If you take all the noise sources that we know and have measured and you add them all up, then you get this green curve over here. And that green curve is reasonably describing what the total sensitivity is, except at low frequency. So at low frequencies, it becomes difficult. And probably there are some technical noise sources like the angular alignment and things like that, that we don't have completely under control. So breaking it down into the dominant ones, then you get the quantum noise here at high frequency. So that is essentially the number of photons that you have. You have your coating thermal noise, it's the blue one here. And then you have your angular control noise. That is the dominant technical noise source that is there limiting the low frequency sensitivity in LIGO. Newtonian noise is over here. So before you would see that, you need it's just, first of all, not a dominant noise source, so you have to fix the other ones, and then hopefully come down by at least an order of magnitude. But if it's very stormy, etc., you might get some evidence of that. But up to now, the evidence that has been seen is machinery in the neighborhood that is making noise and that you find back in your signal. And of course, you can call that Newtonian noise, but I would not look at it that way. I think that's if you have noisy equipment in the neighborhood, you should fix that. So here, yeah.
Maybe you said this, but what's your definition of Newtonian noise?
Yeah, that's so the Newtonian noise is coming from moving, say, mass fluctuations, and that would so then you get a Newtonian interaction. So if I have some additional mass here for the moment, then my mirror will be attracted to that mass excess. And so these density fluctuations you can get typically through seismic fluctuations in the soil. So seismic waves would sometimes increase the density in a certain position and sometimes decrease it. And the mirror would feel attracted to that and would start fluctuating stochastically. You also can have it because of the weather, that you have density because you have temperature fluctuations in the atmosphere. You get density fluctuations, and also that will attract the mirror. So for a detector at the surface, this atmospheric Newtonian noise would limit you at low frequencies. So going below the surface, a few hundred meters, you can get rid of that component to a large extent, but you still are limited by these seismically induced fluctuations. Of course, when you walk next to a mirror, then you are also attracting the mirror. You could call that Newtonian noise. I would say you shouldn't do that. Okay, so that is not something that it has been studied actually. You can calculate that, but that is not the things that we are addressing right now. I'm looking mostly at the effects of density fluctuation due to seismic waves. And
so is there an exclusion zone in things like these telescopes, like no humans should venture within that zone, or even like worms and animals and things like that? You have to.
No, absolutely. If we are in a science mode, you cannot enter the central building, for example. You should not do that. It's not allowed.
Right.
But what about like bunny rabbits?
Yeah.
Yeah, at some point, it's difficult to tell rabbits what to do, but.
No, but I guess I'm asking, can you detect if a bunny?
It depends how close it is. Okay, so we have, for example, to calibrate the interferometer, typically what we do is we take a laser and we put radiation pressure on the mirror, and then you can calculate, if you know the transfer functions, how much the mirror would move, and you can use it as an absolute calibration of your displacement, so for your sensitivity. But we also have a calibrator, which is called our Newtonian Calibrator, where we have little masses which are rotating, and they also will influence the mirror. And once you know the distance, you know the sizes of the masses, etc., you also can use that as a calibration of your interferometer. But these are tiny masses. I think if you don't want to have bunnies running around within, let's say, 10 meters. But if I think outside, if it's like 50 meters away, I don't think it's a problem. Not at our sensitivities right now.
And doesn't matter smaller things like flies and stuff.
No. They're not sitting on the mirror. It depends how close they are.
Sorry, can all these small effects be reduced during the data analyzing? I mean, do you have any idea which type of signal they can make?
Now, you see, if it is machinery that is moving, for example, part of the tower, and it starts shaking, and you can correlate it to that machinery, then what you could do is place a sensor there, measure that, and make a Wiener filter and try to filter it out. And that could be an activity. For example, windmills that would shake the ground, and you could try to put sensors and try to filter that out. At the end, I think if you, what we are studying right now, if you have seismic displacements in the soil, then you put a whole array of seismic sensors. Then you can make an analysis. Typically what we do is make a neural network, and we train it on the interferometer signal, because mostly there is no gravitational wave event in there. And you optimize your network. And then you can use that to subtract your Newtonian noise. We have been successful in doing that. So that is not done in the interferometers right now. We are testing this for Einstein Telescope. And then you can do that right now with a factor maybe 2 to 5. That is roughly what we achieve at the moment.
Okay, thank you.
And because it's difficult, all these seismic waves, they have dispersion, they have mode conversions. Also, even the signal of a windmill is very complicated, because these windmills have resonances, they have 3 blades, and you excite many things at the source of a windmill. Typically, you have several of them, and then these surface waves have huge dispersion. So everything starts mixing. So it's it's a technical problem. It's not a simple technical problem.
Thank you.
And while you are still at this slide, can I quickly ask a little bit about the coating thermal noise and the quantum noise? Okay, so
yeah.
So these are typically high frequency noise, right? So I would think so at low, would they not average out at low frequencies? Like when you're measuring a signal for a long time, sometimes in the up and down in the noise kind of averages out. And so that
this is a power spectral density. Yeah? if you have a signal, for example, from a continuous wave, which you can integrate for months, that will be a different story. Then the sensitivity that you see in the vertical axis right now is typically for a signal of a second. But if you would do it, if you can measure longer, then effectively your sensitivity is much better.
I see. Okay, no, thank you.
Yeah. But these, what you assume here is that these noise sources are incoherent, and you take the noise powers and you add it.
Okay, yeah.
If you go then to the different sites, so here you see the two LIGO sites on Hampton and Hanford and Louisiana. And you have the Cargara site. So the Cargara is in purple, that's the lower one over here. And you clearly see by going underground, things become significantly quiet. So you gain about an order of magnitude, or maybe even more when you go underground. Virgo is quite noisy because Virgo was built on soft soil. So that soil features low wave speeds for seismic motion, and that amplifies the amplitudes. So and that is what you see back here. And so LIGO is more on a rocky soil in Hanford, and is in that sense a bit better. So here you see the low frequency sensitivity of Virgo in purple compared to the two LIGO detectors. So you see below something like 20 hertz, they are the same, or they're similar. And it's only when you go to higher frequencies that you see Virgo is much worse, because we didn't have signal recycling, for example. The reason to detect at low frequencies is that with Einstein Telescope, we have a sensitivity that we can measure up to a redshift of about 100. Yeah? If you measure a signal at a high redshift, for example, 10, that means that the signal and the frequencies will all be a factor of 10 lower than if the same signal would be measured at a redshift of 1. So automatically, by measuring at a higher redshift, your signals will shift to low frequency. For example, the first detection that we did typically had a peak frequency around 150 hertz. So if that would be a redshift of 10, that peak frequency would have appeared at 10 hertz. At 15 hertz. So it is if you want to measure at signals at high Z, then you should have good low frequency sensitivity. The same is true if you want to measure more massive black holes. The more massive the system, it will appear at the lower frequencies. So if you want to look at the early universe and see how these massive black holes were built up for maybe hierarchical matter from lower masses black holes, then you would also like to study these intermediate mass black holes. And then again, you need low frequency sensitivity. If you can measure at lower frequencies the same signal, then the signal will be longer in your measuring band. So if you can measure, for example, starting at 20 hertz, or you can measure starting at 2 hertz, then it's almost a factor of 500 that the signal will be longer in your measuring band, which means that you have an early warning time, which is much longer. So for some signals in Einstein Telescope, you can tell about 2 days in advance that, say, the next day a merger will occur. And that is all thanks to the low frequency sensitivity. Another example is if you are interested in looking, for example, at spin precession. So where you have the black holes orbiting, but also you have they are spinning around their axis, but also you have a spin orbit interaction. So then these precessions can be quite slow. And if you want to have that all in your measuring band, you would like to start measuring a lower frequency. So there are many, many reasons why low frequencies are important to realize. And that is why we focus on them at Einstein Telescope. So these are the sensitivities that are realized right now in LIGO and Virgo. And Virgo is not at the design sensitivity yet. So here, this is where we need to go if we want to reach the design sensitivity of Virgo. So that's about 2 orders of magnitude that we still need to improve. And we may mainly have to improve on technical noises. So then the design sensitivity for Einstein Telescope at 10 Hertz is here. So that's, again, more than 2 orders of magnitude. So in total, the improvement at 10 Hertz is 4 to 5 orders of magnitude that you want to achieve. And then here at 10 Hertz, you will be bothered by Newtonian noise. So it's still quite a way to go. And if you would naively look at the sensitivity of Einstein Telescope, you would say, yeah, it's about a factor of 10 better than LIGO Virgo. Then you have to realize that, first of all, LIGO and Virgo are not at their design sensitivities. And second of all, that Einstein Telescope wants to go much lower in frequency. And that is way more difficult to achieve. So here you see the gravity gradient noise, where it would limit Virgo. And in Virgo, it's relatively more important since the seismic motion at the site is higher than at LIGO. But then still you would have to push this down by big factors and also push it to the left if you want to realize the sensitivity at Einstein Telescope. This band over here, this frequency band, is completely limited by Newtonian noise. That's the main noise source that determines this sensitivity band. So we have been studying that, and you might know that there are 2 candidate sites at the moment, and that is in Sardinia, that is the Italian side, and the border region of the Netherlands, Belgium, and Germany. That is what we call the EMR side, and the Euregio Meuse-Rhine side. There is actually also a 3rd site that is being studied right now, and it is in the eastern part of Germany, in Saxony. And so it might well be that when we talk 1 year from now, that there are 3 sites. So I will talk about the seismic studies that have been done in, say, in the border region in the Netherlands, Belgium, and Germany. And we did, so here are the 2 publications. So this one came out in, I think, November or December last year, and this one in January this year. So these are relatively new publications. And what you see over here is that if you measure on the surface your seismic motion, and you go 250 meters deep and you measure, then at frequencies below, say, what is it, a fraction of a hertz, it doesn't matter whether you're on the surface or below the surface, the seismic noise is all the same. But if you go above a few hertz, then you see that on the surface, you have a certain seismic noise. And the difference between this blue and this purple is that one is measured during the day, and this is measured during the night. And that already tells you that this noise is due to human activity. Yeah, people sleep at night, and then it's a little bit quieter. And here is when you go underground. So the suppression factor of the noise, the attenuation factor, is shown over here. So there's no attenuation below 1 hertz, but above you go to attenuations of about 4 orders of magnitude. And especially during the day, about 3 orders of magnitude during the night. And that is the reason to go underground. So here, the surface on the EMR side is very inhomogeneous. So you have hard rock over here, and then layers of different soil until you get to the top where you have really soft soil. And the nice thing about that, if you have these different layers, you have different impedances, and the noise that is created gets reflected off on all these impedance transitions. And in a sense, that is the main reason why this surface noise is not going to the location of the mirror, which is at a depth of about 250 meters. The drawback of this type of geology is that it's very difficult to model, because typically when you talk to somebody in a gravitational wave experiment and you ask about the Newtonian noise, and everybody knows the result by Solson, where essentially you assume a homogeneous half space. Then you take blocks of lambda over 2, and you say these are incoherent. Then you need a displacement measure. So you take one seismic sensor somewhere that gives you a PSD. You plug in the PSD and you get your Newtonian noise. Now, if I put my PSD on the surface, or I put it here, I have a factor of 10,000 difference. So that is not the way to go, because my mirror is here. And of course, I cannot take the PSD next to the mirror, because that would be an underestimate. So what we do is we try to do this in a numerical way. The approach is that we have surface and underground PSDs. We also measure the distribution of the noise sources. Where is the noise coming from? And we do that by networks of seismometers. We measure horizontal, vertical spectral ratios, elasticity of the waves. We try to include all reflections and interference of waves, all wave types, P waves, S waves, Rayleigh waves, loss waves, mode conversion, higher order waves, and etc. And also realistic geology. So that is the ambition that we have. So that is obviously not possible with some method like Solson. You need to do this numerical. So we work together with.
Can I ask something? So it's very, very interesting. So can I ask something? So of course you are taking small elements and doing the gravitational acceleration due to that, I guess, right? To give him. So you are. So as you go down, I see the effect broadening as well, like dispersing. So is it correct to say that the noise, can the noise be flat for hundreds of meters, like not create a relative noise over a certain, is there like a wavelength of the flatness?
Yeah, certainly that is there are wavelengths, but the wave speed for every wavelength is different. So it's dependent. So if you have these Rayleigh waves and the things coming from the surface, they are very dispersive. These wavelengths they are extremely different. I can show you some of that.
Right. Mm-hmm.
So what we did is passive seismic surveys. You see we put a network of seismic sensors here, and also here a few hundred sensors here, or 160 sensors here. And we try to characterize this area. We do both passive surveys and active surveys. So passive means you put your sensors there and you just measure for weeks or months. And if a wave is coming, for example, from this direction, then these sensors will see them first and then these later. So what you can do is you can do interferometry with your sensors, and you can point to where the waves are coming from and what wave speed they have, etc. So we use this to do so-called beamforming. And here you see other sensors that we put there, and then we actively, with a vibro size, start exciting the ground in order to get more power to deeper layers. So we collaborate with geophysicists in doing that. We also collaborate with Shell, because of course they do this for a living. They know so much about these techniques, and they have such advanced software. So we had, for example, our PhD student trained at Shell for a few months before we start doing these measurements. So then once you have this seismic information and also your geology, your information about geology, because we drill boreholes and you can take samples, and TNO is involved in order to do analysis on the samples. The geophysicists know about the layering of the area, and then this is the result of a seismic inversion, for example. And you see that it is quite folded in some areas, which is not good, okay? But that is the way it is. And here you see the locations of the boreholes that we drilled.
Sorry.
Yeah.
Do you consider, I mean, the seasonal variation of the seismicity of the region? Have you considered
absolutely,
this?
absolutely. Yes. We measure. For example, in the publications, you find results over a year, and you see that normally you would expect that in the winter you would have more seismic activity due to more storms and things like that. And we see the opposite in that area, and probably it has to do with tourism, because the area in the south of Limburg is not industrial at all. It is how do you call it? It's a natuurgebied. So it's a protected area for tourism. But when the tourists come, of course, they start making noise, and that is what we see back in the spectrum.
But also, for instance, absorption or drying of the ground because of rain and the snow and so on. This sort of.
I don't think we see that, to be honest. Or maybe we didn't look at that in too much detail. No, I don't think we see that. Okay. I can tell you what we did. So here you see the arrays. So seismic sensors here and another big array here. This array here, and with that you can do this interferometry and beamforming. You also can measure horizontal to vertical spectral ratios, which tells you something about the layering of the soil. So 3D power spectral densities. We measure the polarizations of the wave. What we also can do is measure the correlation. So we correlate in time the signals. If you have a sensor on the surface and a sensor below, and a wave is coming in horizontally, then the signals should peak at 0 time lag. If they don't peak at 0 time lag, then you get evidence of body waves coming from other directions. And so that we used also in combination with day-night ratios to get a handle of a general body wave background. We have the borehole studies, so we measure gamma rays, radiation from potassium, thorium, etc. We measure resistivity in the borehole, P-wave velocity, and all of that to build up a model about the lithology of the soil. So if you want to have the details, then again, this is all discussed in the papers. So then what we do is we take this wave equation that you have and we solve it for this layer geology. So we have a geology consisting of 5 layers. Here, for example, you see this beam forming. So you see signals coming in from different directions on the surface. So these are the angles, the sine phi or cosine phi, the waves are coming in. And the P here is 1 over the velocity projected on the surface. So you see that most of it is coming from the south with a certain speed, actually a high speed over here. You also see that here you see 2 rings. And this is excitation of a higher order mode, a higher order Rayleigh wave mode. So this soil, you also can excite, and that's what these seismic vibrations do. And they excite also higher order modes. You see it again coming back here. Here you see a band, here you see a band, and here you see the dominant band. So you have a fundamental mode, but also you excite the higher order Rayleigh wave modes or low waves, etc. So what we then do is we construct a model where we can reproduce where the waves are coming from with what speeds, so at what frequencies. So we set the sources, and that way we take this wave equation and we solve it with a solver. So typically you can, for example, the University in Leuven has developed a solver, their geophysics department. That is the one we use. It has the drawback that it only can do horizontal layering. And we know that our geology is not perfectly horizontal layer. So we need 3D solvers. They are available at Shell, but of course they're very proprietary. That is the core business of Shell. And then once you solve it, you solve it for U, and U is your displacement field. So U gives you, for every position, the displacement of the mass element as function of frequency. And then once you know that, you can do the integration of all these displacements, because if you have a mirror here and a mass element here, and you know the displacement, you can calculate what the Newtonian interaction is, and you integrate of all the mass elements over all the boundaries, because if boundaries move, it also gives an effect. If the surface boundary is moving up, then air is displaced by matter, and you have to integrate that boundary also. And that is how we calculate our Newtonian noise. And that also allows us to put in caverns and look at the effect of cavern walls and things like that. So this is the approach that we follow. And here you see all the boundary conditions that we use. So the types, and then these waves here are, so when we solve that, we can compare these solutions also to our measurements, to our PSDs and horizontal to vertical ratios, etc., to ensure us that this is indeed a solution that is obeying what we measure. So this is the way we approach that. And then you just integrate. So you can do the integral over the surface wave, so all the noise that is made at the surface, which is the dominant part. The noise on the surface is 1,000 to 10,000 times higher than the PSD below. But then it is reflected off from this geology, and also the surface has a very low wave speed. So that means that the waves have, say, if you look at it as a sine wave in density, it has many pluses and minuses. So from the point of view of the mirrors, lots of effects integrate out. While if the wavelength would be long, then the effect of the Newtonian noise would be much bigger. That goes actually with the wavelength square. That is something that you don't see back in Solz's formula, but that is absolutely happening here. So you see the side is very effective in reducing the noise created at the surface. But what is bothering us is this body wave background, these random body waves that are coming from all directions, and they could be created, hundreds of kilometers away, or by waves hitting the ocean bottom and things like that, and that is determining the noise. So when you look at the Einstein Telescope design sensitivity, then in this range here, it is completely determined by Newtonian noise. That is what we projected, and the side in our border region is about a factor of 2 higher than what it should be. And that is what motivates us to go into these neural networks and using all these sensor networks in order to subtract this noise. And we can do that depending on the frequency by a factor 2 to 5 right now. That is where we are. This is still work in progress, so I'm not going to discuss that part. But I think we will publish that reasonably soon. And then, so that is the approach that we are following. And I think it's
If I may ask you a question. So what is roughly the size of the system which we are integrating out? I mean, it's a mirror, roughly the size of the mirror.
No, we integrate up to at least 5 kilometers.
Up to 5 kilometers, I see.
Yeah, because the thing is that if you, this is an interesting, if you take an infinite space, okay, and you would take a spherical cavity, and you would put a mirror at the center of the cavity, then there is no gravitational field. If you displace it, there's also no gravitational field. In the end, this was known to Newton already 300 years ago. So in an infinite medium, you can move that cavity the way you want, but you will have no Newtonian noise on that object. But all of this depends on the fact that you have spherical symmetry, and that your outer integration boundary, which is at infinity, is creating a field which cancels. If you would take that like a square boundary at infinity, you would generate a field. So in doing these kind of calculations, you have to go quite far out. You could say, yeah, but if it's far away, it will decrease. No, because it falls over 1 over the distance squared, but the area also goes with the distance squared. So it never stops in your gravitational field. And that is why we go quite far and integrate these boundaries. And that's actually, and these boundaries now are either the surface, so you have a mirror, and at 250 meters you get the surface, and the surface can move, and that you have to take into account in your integral. So anyway, so lots of interesting things here.
Thanks, thank you.
There is also a result on from Italy that is shown here. And here again, in this curve, you see the ETD sensitivity. So in this range is the blue line here is the Newtonian noise in that curve. And this is what they calculate. So it's above here and above here and below here. But this calculation is done essentially using the Solson approach. So you take one PSD measurement, the ASD, you plug it in, and the rest are just numbers, and the length of your interferometer, the frequency, and some constants, and then you get your Newtonian noise. So, so that is the result that we have now from Italy.
So here rho naught is just the density of the atmosphere or the ground?
The ground. So the entire rock is assumed to have homogeneous density, which then is assigned the value of rho naught.
Right. So this, you said this should not work so well, right? I mean, from your earlier pictures, this.
No, this should work if you have a very homogeneous you have very homogeneous soil.
I see.
And if you and you make some assumptions. Okay, first of all, that the PSD that you use is representative for that entire half space, and that you only consider body waves, etc., no surface excitations. So, but this is all fine. There is no problem in that, because it is all work in progress. But at some point, let's say 2 to 3 years from now, we will have to choose a site, and this will be one of the ingredients in choosing a site. And then the question is, how much can you subtract with a network? Because then if you've managed to do that, then of course it's not so important anymore what the quality of the site is. But I'm not so optimistic. I think to do maybe a factor 2 to 5, I believe. But I see no evidence right now that you could subtract, let's say, a factor of 100. I just don't see that. But,
sorry, a question. For the selection of the sites, do you consider the general, not the noise that that affect the day-to-day operation of the detector, but this seismology study? I mean, the seismic hazard of the site. Because of damage eventually which can have imposed on the detector, or you don't consider this?
No, so any earthquake worldwide, we typically see also with LIGO, Virgo, and Gagra. And in a big fraction of these events, we unlock the interferometer. So the interferometer has to be brought into operation again. And so it is not that worry. Typically what we see, we have a warning system that if earthquakes are coming, then the power in the control system is increased to hold the mirrors more in place. So that leads then that our sensitivity becomes bad, that worsens, but that we don't lose so much time in relocking the interferometer again. What is a discussion at the moment is that if you have these tiny earthquakes, so you can have like hundreds a year in an area, how much that would cause an unlock of an interferometer, and that you would have to relock again. Typically right now, we lose about 5% of our science time due to earthquakes coming from anywhere. And of course, you cannot build something in a real active region. Because it should not damage the equipment. But then again, we built it in Italy, There is an interferometer built in Japan, and they can operate.
Okay, thank you.
Okay, so anyway, so hopefully all of this will lead to this green sensitivity curve. In purple, you see a Cosmic Explorer. And here in gray, you see the best that we have achieved so far. So it's a challenge. And the challenge is especially there at low frequency, because I showed you the factor of 10 to the 4th, 10 to the 5th that we need at 10 Hertz, but I didn't even talk about 2 or 3 Hertz, because that's even, it's astronomical. And if it all works out, we will have a range up to a redshift of 100, which will be fantastic, of course. And also many of the events will be measured up to large redshift with very high signal over noise ratios. So compared to LIGO, Virgo, Carcara, we will have a sensitivity that will bring us to the era of the so-called dark ages, before the formation of stars. And let's see if there is indeed a huge activity of black holes there or not. We will find out. And typically within a few years, we will collect about 1 million merger events, so distributed through the entire universe. So you can do beautiful astronomy, astrophysics, cosmology, etc. So I will not go into the physics, it's too tempting. Then at the same time, there will be also many other instruments operational. And so in the correlation between these data sets, there will be quite some relevant information also for multi-messenger physics. And let me finish with this slide here that gives you an impression about the Einstein Telescope. So the triangle with arms of 10 kilometers. Here you see a corner station. So there are many underground caverns. There are 6 tubes underground, 4 from the 2 overlapping interferometers and 2 from the filter cavities. Clean rooms below all the interferometer items, so that you can work in the clean rooms and then put them in the vibration isolation towers. You see blue towers and red towers. That has to do with the low frequency, the high frequency interferometer, because part of that is cryogenic. So let me stop here.
Thanks. Thank you very much for this very exciting and very informative talk. We have never heard such excellent, noise aspects of the talk when it goes into detecting gravitational waves. It's amazing. So please, we have already had many questions. So please, from the audience, if you have any question, this is the right time to ask. Just
yeah. So I have a somewhat general question, maybe not too much related to the talk. So when we receive gravitational wave, we can infer some properties of the source, which can be, say, binary neutron stars or black hole. So gravitational wave must carry information, and then from black hole we know that its mass is proportional to its entropy. So I'm just wondering if the information transmission mechanism is well studied in this case. So let's say how is the reduction of the black hole's entropy compared to the information carried by the gravitational wave? Is this
yeah, okay. What has been done is that people have looked at the masses, because the masses and the area. So the idea that the area always should increase, so that the sum of the initial black holes, the area, should always be less than the total area at the end. So that is because of entropy. And there are publications about that. I think we never saw a deviation from that, because that would be big news. Yeah, other things that have been done is of course looking at the mass of the graviton. I guess you know that. Yeah, so we have put a limit on the mass of the graviton, because you can look at the dispersion of the gravitational waves and use that as a handle on the mass. So of course we don't know if the graviton exists or not. We cannot make a statement about that, because we don't detect the graviton. But if it exists, then we know that the mass is smaller than 10 to the minus 22 electron volt.
I see.
That has been determined. Right now it's already a few times 10 to the minus 23 electron volt. And already the first measurement gave a limit that is 10,000 times stronger than the limit we have on the mass of the photon. Because everybody says the photon is massless. Yeah, sure, but what is your experimental evidence? And the experimental evidence for on gravitational waves is already 10,000 times stronger than the evidence that we had on the photon.
Okay, yeah, thank you very much. Yeah,
And there are so many things to discuss here, which are interesting, and also how it would how these waves would travel through the vacuum, etc. What effects that could have on the properties of the waves. So typically, what we do is we study all these expansion coefficients that you have in your post-Newtonian expansion. And in principle, there are many of them, but every expansion coefficient should only be a function of the two initial masses, the two initial spins, and if there would be charge of the charge. But let's forget about the charge for the moment. So that means that there is a contingency, a consistency that you can do on a check on all of these post-Newtonian coefficients. And you can compare that up to now, when we compare it to general relativity, it is all agreeing with general relativity. But of course, it could be that at some point, because right now we talk about a 10% measurement, but at the end with Einstein Telescope, you will do sub-per-mil precision, really high, very high precision measurements on these coefficients. And maybe we get some evidence then. But at the moment, it's all consistent with GR.
Yeah, thank you.
In the papers that you have written, is this data fully available, like the density fluctuations caused by a seismic wave profile?
Yeah, and also all the seismic data that we took is publicly available. So everybody can take that data, do their analysis, and
right.
The thing that is problematic is to get the solvers to solve the wave equation, because these are commercial products, or you have to talk to Shell to see if somebody can help you.
Right. Solver means even if they give the density and things, when you mean the integration from there.
You need to, so you need to, from your seismic measurements, you get a model of the subsurface in terms of layers. And every layer has thicknesses and densities, but also every layer has the speed of the waves as function of frequency. So the dispersion is also in there, and that is what you need. So then you need to give that to as boundary conditions to solving the differential equation for the waves. And these solvers, so we use a commercial solver for that.
Okay, and why is that necessary? So these are still second order, like d squared, dx squared.
Yeah. And the reason that you need a solver is that at the end you want to have the displacements of every mass element everywhere, and you integrate over everywhere.
That's true. That's true. Okay. Yeah, so it would be nice for, so, we look at much smaller interferometers with some kind of mesoscopic masses. So it would be, I mean, we have looked at things from like clumpy things like aeroplanes or animals. And then we have looked at Salson-like thing everywhere integrated, but it would be nice to look at this kind of thing, maybe discussing with
we can do that.
And just check what is the effect.
So
I was already talking to Anupam that I would enjoy coming to Groningen and visit him, and then we would have time to discuss.
Sure. So Joe, one question: did you guys look into the around 1 Hertz? By any chance?
Yeah, sure. We calculate also at 1 Hertz. Yes.
Because that might be very interesting for a small interferometer, which I think Sugato was mentioning now also. Yeah.
One question. Is there any overlap between the frequency domain of Einstein Telescope and LISA?
No, there is not. Yeah, that is a very interesting one. But so I think that there is a gap from 1 hertz down to maybe, what is it, 10 minus 2 hertz or something. So that is where both don't have very good sensitivity. That is where people in the future would like to have a Big Bang observer. So a special mission with shorter distances between the satellites. So, but what we can do is that, of course, when, for example, the first event that was measured by LIGO, that would also have been seen by LISA, and probably something like 1.5 years earlier. And you could then point and predict when it would be observable with Einstein Telescope. Then you have a very long lever arm in time to look at these signals and maybe phases or things like that.
Yes, sure.
So you can do things together, but there's no overlap.
And also you can arrange all the other optical, radio, and so on and so forth. Huh?
Yeah, but that is they measure at completely different frequencies. So they take all the optical instruments can see that, but if you have black holes, they don't see anything. And with LISA, I think it's mostly black holes.
Sure, but if they are something that I would be very interested in, if there is any mass around the black holes, baryonic mass around the black holes, which somehow during the merger make an explosion jet or something else, it would be very interesting to be able to observe them.
Yeah. No, that is the people are looking at that. That is right. Yes.
Thank you.
So is there any other question from the audience? Well, if not, then yeah.
Well,
please.
Professor, I have a question about the mesoscopic interferometer mentioned by Professor Bose and Mazumdar. So how to deal with the gravity gradient noise in mesoscopic interferometers?
I think it's probably something similar that you have to do. You have to do that analysis. At the end, it is indistinguishable from a real gravitational wave. So for our interferometers, whether it's a gravity gradient signal from seismic or whether it will be cosmic, there is no label that you can use to distinguish. So you have to do that analysis, I think.
Yeah.
But what you can do is that if it's seismic, it will correlate probably with a seismic sensor. And you use that correlation in order to maybe train networks and subtract it. And I know that also in satellites, they do shaping of equipment so that you don't, because the coupling is quadrupole, and you try to suppress it that way. But I guess you know all of that.
Is there some published literature on the subtraction of noise kind of thing, some kind of review or easily accessible?
Yeah, I wrote something about that. I can mail it to you if you want.
That'll be great.
Sure, yeah, that would be very nice. Yeah. So we have a community where we are talking about gravity gradient noise, and also it would be wonderful for us to know. Yeah.
Sorry, can I ask another short question?
Yeah.
You didn't mention what is the resolution that you expect from Einstein Telescope on the sky for finding the place of the source on the sky?
Yeah, so at the end, what we would like to have is again a global network, and but I think the best we can dream of is in the order of 1 degree, 1 square degree. It will not be much better than that.
Yeah, but yes, I mean, as you said, a global network would be very interesting, but the frequency range is not completely covered by other present, I mean, existing detectors. This is the problem.
Yeah, no, that is true. And with the existing detectors, you when the redshift is above a few, they don't see anything anymore.
Yeah.
So so the hope is that we would get a Cosmic Explorer in the US, and there may be one more detector or an upgraded other detector.
Okay.
And there are some ideas, but that is not concrete at the moment.
Yeah, but this is, I mean, it's for very long time.
Yeah,
30, 40 years, something like that.
Yeah, we hope if Einstein Telescope that if everything would go according to plan, maybe that around 2035 we would start doing commissioning and maybe the first short science runs. But then it really has to go fast. Then we have to decide on the site in 2 to 3 years from now, and we have to get the funding together, and all of that is non-trivial.
Yeah.
But you know, in the Netherlands, we're trying right now. There is a funding request in for more than 900 million at the moment, and the same in Italy.
Yeah.
So it's being discussed.
And with the present political situation in the world is
Yeah, it doesn't help. No.
yeah, it does not help for scientists.
No, it's terrible.
Yeah. Thank
Good.
you. Thank you very much.
So, so please, if there is any other last minute question from the audience. If not, then we should thank Joe. Joe, it's really wonderful. I think you gave a fantastic talk, very insightful for all of us. Thanks. Thank you very much.
Yeah, it's nice to do it. Thank you.
Very much.
Thank you.
Let's keep
Bye-bye.
in touch. Bye. Yeah.